Okay, thank you, sir. सर मैं निकल रहा, ठीक है? हाँ हाँ सर, कोई इशू नहीं. थैंक यू, सॉरी फॉर डिस्टर्बेंस. Okay, so this is the relationship between reference current and I naught current in the current mirror. Let's see some more circuits which are important for the exam, and that circuit is one more circuit we are looking is Darlington pair circuit. The next circuit is known as Darlington pair. So what we can say in Darlington pair, the first stage is this. We are having one this circuit. What we can say, input is applied at base terminal, and output we are taking from emitter terminal, and this emitter is acting as a base for the second transistor. So you can say this is acting as a base. So This is VCC. This is RC, and we are taking our output across this. This may be some DC supply. So this pair of transistor, when you are giving input to the base terminal and output to the emitter terminal, this is common collector. And when you have input at base and output at collector terminal, this is common emitter. So this is the kind of circuit having input at collector terminal, common collector configuration, and taking output from common emitter. This type of circuit is known as Darlington pair circuit. So let's draw the small signal model for this Darlington pair circuit, and let's analyze how we can analyze the Darlington pair circuit. So let's start. We are having one small signal model, so we can start with the hybrid pi model because there is no resistance on base terminal. We are starting with the hybrid pi model. First we are having one R pi 1, and this is B1, the base of the first transistor. Then we are having one emitter terminal. Then we are having one collector terminal, which is GM1 into VBE1. Then we are having one collector terminal. Okay. This is for first transistor, and what I can say, the base of first transistor is connected to Vi, so you can say there is one source which is known as Vi. Then the emitter is connected to base, so I will start second circuit from here. This is VBE2 R pi 2. Then this emitter is connected to ground, so I am connecting it to the ground. Then this is GM2 into VBE2. Then we are having one resistance which is RC. So and this is what? A small signal equivalent. a small signal equivalent of the circuit. So I am interested in input resistance of the circuit. What will be the input resistance? The first most important thing in this input resistance of the circuit. So I can say input resistance so you can say what is input resistance of the circuit when you leave this when you remove this supply and look inside, then this resistance is known as input resistance. So what we can say, the first current is input current is IB1, so this is IB1 IB1, then this current is 1 plus beta times of IB1, which acts as a IB2. So we want the ratio of input voltage to input current, so I can say the resistance is R pi 1, this resistance plus the resistance of this terminal is, resistance of the second terminal is equivalent to R pi 2 into 1 plus beta. This is R input. This is the input resistance of the circuit. So this is very important. Higher input resistance means they're good for a voltage amplifier. So no problem about it. Now we are interested in this is the point from where we are taking output. So the characteristics of the Darlington pair is input resistance will be higher. Okay, can I say the current gain of the circuit? If this current is input current is IB, then this is 1 plus beta times of, okay. So you can say current this circuit can be written as this is written as beta 1 times of IB1. So I can say here current is what? IB plus this current is IB, this current is 1 plus beta 1 times of IB, then this current is 1 plus beta 2 times of IB. So what is the current gain of the circuit? IE1. So let me write this. IB2 is equivalent to IE1, or what I can say, IB2 is equivalent to 1 plus beta times of, या इसको beta 1 भी लिखते हैं if you want to differentiate beta 1 and beta 2, IB1, and IC2 है ना, is approximately, let's say, IE2. So this is 1 plus beta 1 times of 1 plus beta 2 times of IB1. So what is the current gain of the circuit? Because output current is IC2 and input current is IB1, and that ratio comes out to be 1 plus beta 1 into 1 plus beta 2, which is beta 1 into beta 2 approximately. So this is a very popular expression. A high current gain is the characteristics of this circuit. You will get a high current gain of Now let's start with the very important topic known as MOSFET circuit. The new topic for the session is MOSFET. We are starting a new topic known as next topic is MOSFET circuit. So let's start with the MOSFET circuit, how this circuit will work. So we can say the full form of the MOSFET is metal oxide semiconductor field effect transistor. So transistor means again transfer resistors. The phenomenon is same, but now we are having uh, uh, the current is independent to the problem with the BJT is the temperature, because reverse saturation current ICO is a strong function of temperature. So to avoid this, we are having a new scheme which provides the same result or better result, is metal oxide semiconductor field effect transistor. So what I should say, in MOSFET we are having in MOSFET let's see the construction of the MOSFET. Okay. So first we are taking one P-type substrate. uh, Let's see the basic fundamental related to MOSFET. इसके fundamentals क्या हैं वो देखते हैं. Then we will talk. So this is P-type substrate. We are taking one P-type wafer, very lightly doped material. You should say this is P minus is a type of doping here. And what this represents? This represents the lightly doped, very lightly doped material. This terminal is known as body terminal. Then one more terminal we are having here is known as highly doped N plus, N type doped. And then we are having this is oxide. What we are saying, this is metal oxide semiconductor. So we are having all the ones. So we can say this is one enhancement type MOSFET. So what I can say, we will discuss that what MOSFET is, how many types of MOSFETs are available. So this is one enhancement type MOSFET. Enhancement type. This is one enhancement type MOSFET. So what you can say, this terminal, this is So what we are having? We are having metal oxide semiconductor. So you can say this region. This region is known as SiO2, which is oxide, and a metal is here. यहाँ हमारे पास एक metal होता है. So first we are having metal. This is metal. This is oxide, and this is semiconductor, lightly doped semiconductor. That's why this is known as MOSFET. This is three-terminal device. The one terminal, this terminal is known as, this is symmetrical device, but this is known as source, which is equivalent to meter in the BJT, which is equivalent to emitter in the BJT. One more terminal is drain, which is known as collector in the BJT. And the third terminal is drain terminal, which is base in the BJT. So these are all terminal, and this is basic structure of the MOSFET circuit. So this is same as your bipolar junction circuit, but in this time the parallel electric field, what I can say, the electric field in this direction this is the direction of electric field. इसको हम समझने की कोशिश करेंगे. So what I can say, the width of channel is modulated by, है ना, यहाँ एक channel बनेगा. We will see that how we can form this channel. So what is the idea? The width of channel is modulated by electric field perpendicular to the channel. जो इस डायरेक्शन में चैनल बना हुआ है उसमें एक परपेंडिकुलर इलेक्ट्रिक फील्ड. सो व्हाट आई कैन से, इफ यू आर हैविंग दिस इज द डायरेक्शन ऑफ चैनल, है ना, तो इलेक्ट्रिक फील्ड कैसी होनी चाहिए? द इलेक्ट्रिक फील्ड मस्ट बी ए परपेंडिकुलर इलेक्ट्रिक फील्ड, है ना. यू कैन से दिस इज चैनल and this is the value of electric field. So this is the fundamental idea for MOSFET. Now what I can say, let's say let's say the types of MOSFET. So what we can say, MOSFETs are MOSFET can be divided into the two categories. MOSFET को आप दो कैटेगरी में डिवाइड कर सकते हैं. The first category is known as enhancement type MOSFET. Enhancement type MOSFET, or also known as E-type. Or second MOSFET is known as depletion type MOSFET. Depletion type MOSFET. Or also known as D-type. So first one is enhancement type MOSFET and second one is depletion type MOSFET. So in enhancement type MOSFET, the VGS, the gate to source voltage, one voltage is responsible for a channel, है ना? Channel is developed in enhancement type MOSFET. What we can say? Enhancement type MOSFET, channel is developed with the help of, by means of electric field, or we can say by means of VGS. A channel is developed. And one more MOSFET is we are having D-type MOSFET. So what you can say? Voltage is responsible for depletion of a grown channel. These MOSFETs are known as normally off MOSFET. Normally on, because a fully developed channel is available, and this is known as normally off. So these are the two types of MOSFET available for us, normally off and normally on. These are the two types of MOSFET which are available. Further, you can classify enhancement type MOSFET in two categories. The one is N channel MOSFET and second one is P channel MOSFET. You can say further we can classify the MOSFET as a N-channel MOSFET and P-channel MOSFET. Which is popularly known as NMOS and PMOS. Likewise, we can have the two varieties in depletion type MOSFET. पहले से एक चैनल बना हो तो डिप्लीशन टाइप, नहीं बना हो तो एनहेंसमेंट टाइप. So this is N channel and also P channel MOSFET. So this is the idea for the MOSFET circuit. This is the types of MOSFETs, and by combination of these two we can have the CMOS. So let's analyze what we can say. First I am taking N-channel MOSFET, the construction of N-channel MOSFET. One terminal we are having is bulk terminal. So this is P-type, lightly doped P-type region. Here we are having heavily doped P junction, N plus, heavily doped N plus junction. Then we are having इसके सारे पॉइंट्स आप ध्यान से देखें कि this is metal, है ना, this is metal. This terminal is known as gate terminal. Okay, so we are having three terminals: gate, source, and drain. This terminal is known as source terminal, and in this, the source is always connected to. In this, source is always connected to bulk, and these two are connected to ground. Why this is so? Because you can say there is a diode. यहाँ एक पीएन जंक्शन फॉर्म हो सकता है. इक्विवेलेंटली आई कैन से a diode can form here, और जब पोटेंशियल अप्लाई करेंगे तो दिस डायोड कैन बी रिवर्स बायस एंड हैवी करंट कैन फ्लो इन पैरेलल टू इलेक्ट्रिक फील्ड. जबकि हम MOSFET एक्शन के लिए क्या चाहते हैं? वी वांट इलेक्ट्रिक फील्ड परपेंडिकुलर टू द वी वांट द चैनल परपेंडिकुलर टू द इलेक्ट्रिक फील्ड. पैरेलल टू द इलेक्ट्रिक फील्ड चैनल से क्या हो जाएगा? डैमेज हो जाएगा. नाउ तो मुझे सर्किट में जितने भी वोल्टेज अप्लाई करना है, आई विल अप्लाई ऑल द वोल्टेज विद इन रेफरेंस विद द बल्क टर्मिनल एंड सोर्स टर्मिनल के रेस्पेक्ट में अप्लाई करेंगे. सो यू कैन से दिस इज सोर्स टर्मिनल, है ना, इसके रेफरेंस में अप्लाई करेंगे. सो व्हाट वन वोल्टेज आई कैन अप्लाई इज VGS. One voltage we can apply to this is VGS. So there is a ground on end, and a negative voltage is applied at this terminal. VGS. So I can say this is VGS can be written as G is positive. वहां भी आप ऐसे ही करते थे. बेस एमिटर जंक्शन is positive, and so I am saying this is VGS, and one more voltage we are having at VDS, है ना. With respect to source only, so I am taking another voltage is VDS, which is ground here. So when we increase VGS, the first what we want to see, the effect of VGS on MOSFET. The first point is effect of VGS on MOSFET. So what I can say, there will be a इलेक्ट्रिक फील्ड. दिस इज, ये बैटरी का पॉजिटिव टर्मिनल है. ये क्या सप्लाई करेगा? विल सप्लाई होल्स. यहाँ होल्स होंगे, एंड वी आर हैविंग dielectric SiO2 in between. So to compensate this positive charges, a layer of negative charges will form here. ठीक है, and a layer of negative charges will form here, and this layer is known as channel. यहाँ जो एक layer form होगा, a layer of electron, this layer is known as ठीक है, और यहाँ N और P जंक्शन बनता है तो दिस विल फॉर्म ए डिप्लीशन लेयर. तो यहाँ क्या बन जाएगा, यू विल गेट अ डिप्लीशन लेयर हियर. यहाँ क्या मिलेगा आपको, यू विल गेट अ डिप्लीशन लेयर हियर. And when you increase VGS, this is proportional to width of depletion layer. जितना ज्यादा आप VGS को बढ़ाओगे, डिप्लीशन लेयर का विड्थ भी क्या होगा, correct? So in effect of VGS, है ना, the width of channel increases. Huh? Now आप कब बोलोगे कि what is the value where you can say the channel is formed and that value is given by manufacturer, उस value को हम बोलते हैं threshold value ना, VGS. There is lot of meaning of based on physics level, EDC में आप पढ़ेंगे. The minimum voltage required for channel formation known as threshold voltage. The minimum voltage is required for the channel formation is known as threshold voltage. ओके, सो दिस इज इफेक्ट ऑफ VGS। और पहले जंक्शन को हमने क्या करना है, फॉरवर्ड बायस करना है। सो आई एम फॉरवर्ड बायसिंग फर्स्ट जंक्शन। दिस इज व्हाट आई कैन से, दिस इज नथिंग बट द फॉरवर्ड बायसिंग ऑफ फर्स्ट जंक्शन। दिस इज forward biasing of input junction. Then we will provide a reverse bias to the output junction. Or better to draw this in this way. Second junction is reverse bias. So we can say this is N. So I am connecting this VDS. So first junction forward bias and second junction reverse bias. And what is the effect of increasing VDS? So what I can say, we can say that this terminal will supply the positive charge carriers, and a current will form because of VDS, and this current is from drain to source current will form. So we can say this is IDS. So what I can say, the maximum recombination is at drain side, और यहाँ जाते जाते recombination कितना हो जाएगा, minimum हो जाएगा. So what I can say, due to VDS there is a recombination, और recombination होगा तो you can say there will be change in the width of depletion layer. कि अब क्या बोलूंगा मैं, कि जो जंक्शन है जिसको आपने रिवर्स बायस किया है, वो रिवर्स बायस नॉन सिमेट्रिकल हो रहा है, कि दिस इज मैक्सिमम रिवर्स बायस इन ड्रेन साइड, एंड यहाँ मैक्सिमम रिवर्स बायस होगा और यहाँ मिनिमम रिवर्स बायस होगा. VDS का वैल्यू और बढ़ाया तो व्हाट यू कैन से, दिस विल बी द मोर रिवर्स बायस इन ड्रेन साइड, है ना. सो रिवर्स बायस इज मोर in effect of VDS, what we can say, junction is more reverse bias in drain side. So there will be voltage where this channel is pinch off, and there is a relationship जिसकी derivation की तो हमें जरूरत नहीं है, but what we can say, there are three, and we are having one symbolic representation also. A symbolic representation for MOSFET. It's a 3-terminal device. One terminal is gate. And gate and remaining body is isolated. So you can say this terminal is known as gate. This terminal is known as drain. And this terminal is known as source. So 3-terminal in the transistor. This is known as N-channel MOSFET or NMOS. This is known as N-channel MOSFET or known as NMOS. One more symbolic representation for PMOS. And one more important thing, there is no current from gate terminal. Ig is always equivalent to 0. The only possible direction of current is given by this. And this current is IDS. You will get the current from drain to source. इस एरो के डायरेक्शन में करंट फ्लो होगा. In of course in forward active region or we will say in flat region. Now one more is PMOS, and what we can say, the symbolic representation for PMOS is given by this. We are having one so you can say this is drain, source, and one more terminal is known as gate terminal. So you can say we are having one gate terminal. And we made a mistake here. Let's remove this. So this is PMOS. And this arrow represents the direction of current, then Ig is also equivalent to 0. So gate current is always equivalent to 0 because of, ideally it's a 0 because there is some current because there is no perfect dielectric. In दोनों के बीच में क्या है? You can say there is dielectric in between, but okay, you can say that this offers very high resistance. When you connect a supply at gate terminal, this will offers a very high resistance. So this is the idea for the NMOSFET, NMOS and PMOS. This is, you can say, the first one is known as N-channel MOSFET. And this is known as P-channel MOSFET. This potential is known as VGS, है ना? And this potential here is known as VDS. ठीक है? So we will talk in this terms, VDS and VGS की term में बात करने वाले हैं. So what I can say, for n channel MOSFET, we are having the idea, writing the answer for n channel MOSFET. So what I can say, for n channel MOSFET, NMOS, I am writing the relationship between voltage and current. So we want relationship between voltage and current. वोल्टेज और करंट के बीच में क्या रिलेशनशिप है वो हम जानना चाहते हैं. So first mode is known as cutoff mode. Whenever VGS is less than VTH, इसका मैन्युफैक्चरर बताएगा आपको कि VTH का वैल्यू कितना है. Whenever VGS is less than VTH, this mode of operation is known as cutoff. And the value of IDS is equivalent to 0, क्योंकि चैनल ही फॉर्म नहीं हुआ है और चैनल फॉर्म नहीं हुआ है तो कोई करंट का स्कोप ही नहीं है. So you can say this is the very important mode of operation. Then next operation is, this is first. Second, we are having VGS is greater than or equal to VTH. and VDS is less than or equal to VGS minus of VTH, है ना? In this case, the current in the circuit is known as mu n into Cx. Now COX is ऑक्साइड कैपेसिटेंस, है ना? सभी का हम लिखते हैं अभी क्या क्या मीनिंग है. VGS minus VTH times of VDS minus of VDS square divided by 2. This is the idea. Mu n is known as mobility of electron oxide capacitance. W is width of the MOSFET. Length of L is length of channel, and this W by L ratio is always also known as aspect ratio. And then you can modify this relationship. Okay, when VDS is less than equal to भी नहीं. And third is when VGS is greater than VTH and VDS is greater than or equal to VGS minus VTH. Then what I can say, the current is 1 by 2. Just replace this VDS by VGS by VGS minus VTH into mu n into COX into W by L into VGS minus of VTH whole square. This region is known as saturation region. This region is known as linear region, or also known as triode region. It's a very popular name. And the first is cutoff region. So these are three mode of operation for the MOSFET. और ये रूल केवल किसके लिए है? These are the rules for NMOS, है ना? These are the rules for NMOS के लिए हैं ये रूल, है ना? This is for NMOS. So in tomorrow's lecture, we will go through the PMOS transistor, the voltage current relationship between P for PMOS transistor, and we'll discuss the biasing of MOS. You know, tomorrow is the day for biasing. Biasing of the MOSFET. So tomorrow will be PMOS and biasing of MOSFET.